All right, good afternoon, and here we are for yet another lovely session of ENGR 2302 Engineering Dynamics. And so today we're going to begin with the next chapter of the Beer Vector Mechanics book, and this is chapter 12, which will be the second chapter of the course. And of course, this is the fourth lecture in the series, and this is part 1 of lecture 4. All right, so let's begin. Now, previously we've been working with the kinematics of particles, and we remember that kinematics deals exclusively with the path of objects, ignoring what kind of forces and masses are involved with those paths. Instead, we want, now in this chapter, we're going to be looking at the kinetics of particles. Not kinematics, but the kinetics of particles. So, let's see here. I just want to check we're rolling because I'm always paranoid about that. So we're going to be looking at the kinetics of particles. So what does this come down to? Kinetics of particles. So we're still looking at particles. We're not looking at rigid bodies. We're not looking at things that have actually have size yet. So nothing's going to be rotating yet. But now we're looking at kinetics, not kinematics. So kinetics of particles is the name of the game. The kinetics of particles. Kinetics of particles. So, in kinetics, we're actually going to be looking at the forces acting on particles, not just the accelerations or velocities. With kinetics, we consider forces or masses, forces and masses, not simply position, velocity, and acceleration. And acceleration. Additionally, however though, we are still dealing with point particles, so this therefore no rotation. We're only looking at translational motions, still dealing with point particles, so therefore no rotation. So we don't need to worry about torques yet or anything like that. We will get there later in the semester. But right now we're looking only at point particles. And then also no consideration of energy, momentum, etc. So we just slowly build this up and we work one piece at a time. The whole idea with dynamics, with the dynamics course, is we start very simple. We start with we start only with the paths of objects, the kinematic paths of objects, of particles, the kinematic paths of particles. Then we start looking at what forces cause those particles to move in those paths. Then we start considering things like energy and momentum, and then eventually we move on to then we eventually move on to things besides point particles. So we'll actually have rigid bodies. We'll have things that actually can rotate, can rotate about a center of mass. We'll consider center of mass, all of those things. So we have torques, mode of inertia, all that good stuff. And we also, and then finally towards the end, we actually deal with vibration and damped vibration and all of those kind of things. So that's sort of the capstone of the course when we start actually looking at vibration, which is something you can actually, you may actually take entire courses on later in your academic careers. Okay, so kinetics of particles. What this is all going to come down to is, of course, Newton's second law. And Newton's second law, in case we need to remember, Newton's second law Newton's second law, of course, is the sum of forces is equal to mass times acceleration. Sum of forces on an object is equal to mass times acceleration. F equals ma. So again, if the what this basically says is if the resultant force, so again, sum of forces, this is the resultant force, the vector sum of all the forces on the body. Vector sum of all forces on the body of all forces on an object and of course basically this just says is if the sum of forces is not equal to 0, then an object undergoes acceleration proportional to mass. Or inversely proportional to mass, I should say. Inversely proportional to mass. Inversely proportional to mass for a given force. For a given force. And that's another way we could phrase it, but there are many different ways we could phrase this. The basic idea is just the sum of forces is equal to mass times acceleration. Mass times acceleration, I should say. And also, another key of this is that we need to consider something, we need to consider a reference frame. So, this must be expressed, these forces and accelerations must be expressed in relation to an at-rest, or inertial is the key word. You'll hear this a lot. Inertial reference frame. Reference frame. So our reference frame, we must be able to define it as stationary. So it will not have, the reference frame that we're going to be defining our forces and acceleration relative to will not be undergoing any rotation or translation. Although in reality, every object is moving, of course. Everything is moving, as we've seen. Everything in the universe is constantly moving. However, there's always going to be some amount of, there's going to be some, we need to define something as not moving. Also, on a related note, speaking of moving in the universe, did you all hear the news on yesterday about the planets? This is in dynamics class, so why not talk about this? This is actually kind of cool. This is actually a very good application of Newton's laws. And actually, it's not quite for point particles, but very similar. But there is a system called TRAPPIST-1. You don't need to write this down if you don't want to, but it's kind of cool. Basically, this was the discovery of had a few key things. The discovery was essentially this is around a cool white dwarf star. Cool white dwarf. These were the key things. They found 7 Earth-sized planets orbiting around the same star. And 3 of them are in the zone that could sustain liquid water on the surface. 3 of them in the habitable zone. So those were the key findings. And also a real cool thing about it was because they are orbiting this dim star, a white dwarf is a very, very, very small, cool star. This is a star that is barely large enough to maintain fusion. And that actually means it will last a very, very long time. It'll burn for much longer than the sun will. But anyway, the cool thing about it is that, or at least artistically or aesthetically, the thing I thought was cool about it was that this, because they're, how can I say? Because they're all kind of huddled close to the star, a white dwarf star will, not a white dwarf, a red dwarf. What am I saying? Cool, what am I saying? Cool white dwarf. No, that's very, very wrong. Cool red dwarf. Very different, sorry. A cool red dwarf. And what is really cool about this, what is so interesting about this artistically is that because these are all huddled very close to their stars, and smaller stars can have more sustainable orbits really close to the star themselves, and so artistically, what would be cool about this is that if you were standing on the surface of one of these worlds, the view in the sky would be absolutely amazing, absolutely incredible. Like if you look up in the sky of Earth or any planet in the solar system, the other planets appear as just little bright stars, essentially just pinpricks of light. If you want to get a feel for what these would look like, imagine looking up in the sky and seeing, instead of seeing Mars as a little pinprick, imagine a disk twice the size of the full moon and seeing multiple of those in the sky. That is what the sky of these worlds would look like. So absolutely incredible. But anyway, but how that's actually discovered is through the equations of dynamics. I mean, all of this can be discovered. How we know so much about the masses and the velocities and their years and their sizes, it all comes back from these equations of dynamics that we're going to be learning about. Okay, so that has a little to do with dynamics, but it's kind of a really cool news item, science news item from yesterday. So let us look at linear momentum of particle. Actually, you know what? I probably shouldn't have said we're not looking at linear momentum. We definitely are looking at linear momentum. Sorry, we're not looking at. Let's just get rid of that. I never said that. No consideration of energy, but we definitely will look at linear momentum. Okay, so linear momentum of a particle. Yeah, we can't exactly talk about Newton's second law without considering momentum. I thought that sounded a little weird when I said it, but I guess I should be a little more careful of what I say. Okay, so again, so look what happens if we replace, let's say we replace the acceleration by the derivative velocity of the velocity by the derivative of velocity by the derivative of velocity. So what you would get is, well, so I would have sum of forces equals mass times dv dt, because we saw, as we've seen earlier, the velocity or the acceleration is going to be equal to dv dt, and so this means the sum of forces, actually I should say sum of forces here, and this means the sum of forces is equal to ddt, the derivative with respect to time of mv, or which is equal to dl dt, and what is this, dl dt? Well, capital L is not length. L is going to be equal to the linear momentum. L is the linear momentum of a particle. Exactly. See, look, momentum is mass times velocity, and if we're saying if I take the derivative of this with respect to time, I have basically I'm saying d dt of mv is the derivative of linear momentum with respect to time. Linear momentum with respect to time, or just linear momentum of the particle. Here. And so again, when we're talking about v, if you have an object of a certain path or on a certain path, say like I've been drawing a lot of purple paths, so I think I'll continue with that. If I have a object on a certain path here, maybe it has mass m and velocity v. Velocity v here, well, it would have momentum mv. The momentum notice momentum is a vector, and the momentum vector will be pointing in the same direction as the velocity vector, or L.
That's because m is just scalar.
And yes, it's because m is scalar. So if you take v, which is a vector, and multiply by a scalar, you will end up getting a momentum vector that is, of course, in the same direction. Okay, so hopefully fairly straightforward. And then there is another principle we need to consider, and that is the conservation of linear momentum. That is the conservation of linear momentum. You've likely heard of this before, but the basic idea is if the sum of forces on a particle is 0, the linear momentum of the particle remains constant in both magnitude and direction. The L vector is unchanged. Thus, the velocity vector, the momentum, I should say this is constant, L is constant in both magnitude and direction. In both magnitude and direction. L is constant in both magnitude and direction. Okay, so that's the basic idea of this. And now let's talk a bit about units for these. Let's talk a bit about the units for momentum. So let's consider units. Okay, so if we're working with the SI system, so here, basically, actually this is an interesting conversation about the nature of unit systems. There are 4 possible fundamental dimensions. 4 possible fundamental dimensions. And you can see this in dimensional analysis if you take, like, so for example, a fluid mechanics class. There's mass, M. I'll use capital letter for dimensions. There's M, mass, whether that's in kilograms or slugs. There's force, whether that's pounds or newtons. There's length is another fundamental dimension. And there is time, T. Now, these are basically our 4 fundamental dimensions in science. We can express basically any other quantity in these. Well, I shouldn't say any other quantity. We could start talking about fundamental charge, things like charge and that kind of thing. But those do exist in maybe another kind of thing. But in terms of most of our analyses, there are 4 fundamental quantities. These are mass, force, length, and time. Everything we're doing in dynamics, at least, can be expressed as these 4 fundamental quantities. Now, here's the thing, though. You cannot pick all 4 of them arbitrarily. You can define any 3 of them however you want. But then the 4th must be defined according to Newton's second law. Must be defined by the second law. Okay? So let's see what I mean by this. Well, let us look at Newton's second law. Sum of forces equals mass times acceleration. Let us interpret this in terms of basic fundamental dimensions. Sum of forces equals mass times acceleration. Well, if I look at this in terms of fundamental dimensions, this is F equals M times length. Actually, I'll do length times time to the negative 2. Meters per second squared, for example, times kilograms. I can use whatever unit system I want, but I can't define all 4 of these arbitrarily. I can define any 3 of them arbitrarily, but the 4th other one has to somehow relate to the other ones via this law. So, for example, let me give you an example of what I mean by defined arbitrarily. So if I say, let's go back to, again, these are dimensions. When I write them like this, I'm not going to do this fairly often. I'm just doing this. You won't see this a lot in this class. This The brackets like this with F, L, etc. These are sort of fun. These are just talking more about dimensions and individual units. So where I have F here, I could use any unit of force there. And then it would be times a mass times a length divided by a time squared. Okay? So, for example, let's say I wanted to define some really screwy units. Okay? First, I am going to define my new I'm going to define some really weird units. And again, units are fundamentally arbitrary. I can define any three of these arbitrarily, but I can't define all four of them arbitrary. So, what I mean by this is, let's say I was going to create a very selfish unit system. My selfish unit system. Behold, I could say my new unit for length will be a Tanya. It's going to be my height, exactly. I'm going to become the new standard unit of length measurement. Lovely. And then the time, my new unit for time, I'm going to call a commute. This is going to be however long it takes me on average to drive to work. And everybody else is going to have to base all of their numbers around this. We're going to have to rewrite all the textbooks in the world to just reflect my stupid custom unit system. This would be the average time of my commute. I'll measure that, and then we're going to make all the clocks based on this. We're going to read all the physics books based on this. It's all going to be based off of my own selfish unit system. My own average commute time, my personal average commute time, not average across the entire population. I'm being really selfish here. Average commute time. And then I could define my mass. Well, that's just going to be my mass. We're just going to weigh me one day and going to create a big block of metal.
You really want to use your weight as this?
Well, I'm not going to give you the value for it. We're just going to say I'm using my mass.
What do you call it?
That's a good question. We're just going to call it mass. Or actually, can someone think of a better name for this? Yeah, commute. We got to come up with a name for it. What should we call the unit that's just my mass? The Larson. Okay, I like that. The Larson, yes. The Larson will be a unit of mass. One day, we're just going to put me on a great big balance with a big block of metal, and then we're just going to shave pieces off the metal block until that is the same. The scale is in balance, and then we just have now the Larson is defined. My weight will fluctuate like everyone's weight does through the days and through the weeks and months and whatever. But that block of metal will be defined as a Larson. Okay, so it was equal to my weight at some random day, or equal to my mass at some random day. So that is a Larson. My mass on some day. Some arbitrary day. And you laugh, but if you think about it, how did a lot of our more archaic unit systems actually come about? Yeah, if you think about now, the metric system is actually tried to define things in something more exacting. They don't even try to use reference. We don't even try to use reference objects anymore like they used to. There used to be a standard. There's still a standard kilogram, I believe, but there used to be like a standard meter, and this was they would decree that this physical object 1 meter long is 1 meter. Now they try to do things more of define a second as a certain number of pulsations of a cesium atom or something like that, and then 1 meter is the length that they'll say something like that 1 meter is the distance light will travel in a vacuum in so length of a time, whatever, define a relation in a second, that kind of thing. But so those are more modern scientific units, but more ancient units, I mean, think about a foot. What was a foot? Well, you have to, it's not a coincidence that it's called a foot. You have to know that at some point, I don't know whose foot it was, probably a king or something, but there was some leader back in the day who just said, you know what, let's just use my foot, and that became the standard unit of measurement. So I joke about this, but this is actually how a lot of our units came about. I mean, this is, etc. So, for example, we have ounces, pounds. I don't know the etymology of those words, but I'm sure we could look them up. But have you heard of the unit stone?
Yeah.
What is a stone? It's like, is it 12 pounds or 16 pounds? Something like that. It's only used in England occasionally. But it's, you have to know that at some point that was just, people thought that, well, that's about the weight of an average rock in a field, so let's call that a stone. It's this kind of very archaic kind of colloquial units. But anyway, my point is not to illustrate the history of scientific units here. My point is to illustrate that if I do this, I cannot just say, oh, force is going to be something else I like. I can't do that. I can't say, oh, my unit for force is going to be my weight. I can't do that because, look here, force must equal mass times length over time squared. It's not going to work. That relationship will not hold true because I've chose arbitrary time values, I chose arbitrary mass and length values. I cannot do that. It's not going to work with Newton's second law. And so I can define, so I can't do that. I can define any three of these any way I want. I could define force as my weight, but maybe then in turn I'd have to eliminate the unit called my commute, or just eliminate the unit called commute, etc. Or I could define the commute, the Larson, and my weight somehow. Maybe I could let the Tanya be my weight, but then length could not be defined independently of the other ones. It would have to be defined mathematically in relation to the other ones. So we have four fundamental quantities, but we can only define any three of them. So basically we usually don't define, we usually always use length and time. So basically what this comes down to is we have essentially two systems that we commonly use. Because of this, we use commonly either an FLT, LT, or a MLT system. Basically, it's a real pain to try to redefine length and time in terms of something else. It's nice to be able to directly measure time values and directly measure length values. It's very convenient to do that because of all the instances that we measure length and time. It's very useful to simply have there's a great utility in letting time and length be fundamental quantities. So in the various systems, you don't see length and time being used as derivative units, even though you could. So what you tend to see is either a FLT system or an MLT system with things defined accordingly. So what this means is, for example, the SI system, the unit of force is a derived one. Unit of force is derived. So basically the standard SI system is an MLT system. SI is an MLT system. Basically we say, okay, well, I'm going to define M, L, and T as fundamental units, and then we'll define a derivative unit, which is 1 Newton, which is 1 kilogram times 1 meter per second squared, or 1 kilogram meter per second squared. Something like the U.S. customary system is actually an FLT system. The U.S. customary system is an FLT system. Is customary is a, that is really bad writing. Customary is FLT. Namely, basically the fundamental units are, the fundamental units for length, it's feet. Time, it's still thankfully seconds. And then force is the fundamental one. We say pounds. sometimes pound force. And then we derive mass. Derive mass from these. We derive mass from these by saying, for example, 1 pound mass. Sometimes you'll see the term pound mass. 1 lbm equals 1 pound over 32.2 feet per second squared. So 1 pound mass is how you read that. And then we also could say 1 slug, lovely unit, equals 1 pound over 1 foot per second squared, or 1 pound second squared per foot. Isn't that lovely? So that's the basic idea. We can either describe our fundamental quantities in terms of mass, or we can just describe them in terms of force, but we have to pick one and stick with it. All right, so let's look at equations of motion. So with that discussion of units out of the way, let's look at some qualities of equations of motion. So let's look at equations of motion. Okay, so we said that Newton's second law is the summation of forces equals mass times acceleration. Now, however, though, all of this is a vector and this is a vector. And so then we can actually use scalar notation, though, to indicate this, or to analyze this. Can use scalar notation or rectangular components to analyze. And often it can be convenient to do so. Or rectangular components to analyze. So, in other words, instead of saying sum of forces equals mass times acceleration, I can say summation of forces, the summation of forces here, Fxi plus Fyj plus Fzk is equal to m times Axi plus Ayj plus Azk. So I could look at this in terms of rectangular components, or perhaps more useful, I could not have this combined equation, but more individual equations. So I could say something like the sum of forces in the x direction is equal to max. Max. The sum of forces in the y direction is equal to may. And the sum of forces in the z direction is equal to maz. Or I could also express this as the sum of forces in the x direction is equal to x double dot. The sum of forces in the y is equal to my double dot. And then the sum of forces in the z is equal to mz double dot.
That's just like the position vector direct.
Exactly, just the position vector. All of the x double dot is just the position. The x, y, and z double dots are just the position vector derived twice with respect to time. Okay, so moving along then. Here, let's see. Now, there's also something else here. There's also another way to express this, a dynamic equilibrium. Dynamic equilibrium. Dynamic equilibrium. And so an alternate expression of this would be something like this. Another way we can rephrase Newton's second law is the summation of forces vector is equal to, or minus ma vector is equal to 0. Or is equal to the inertial vector. An inertial vector would be one that is basically 0 in all directions. So basically what we're saying here is, with the inclusion of the inertial vector, the system of forces acting on the particle is equivalent to 0. Of forces acting on the particle is equivalent to 0. Acting on particle is equivalent to 0. So you could have an object, and there could be a series of forces on here. There could be F1, F2, F3, but then because I added it over here, I would also add a ma vector, something like negative ma here, a negative ma vector, and all of this would sum up to 0. And so when something is, all of this is equal to 0, what this means, what the state is referred to as dynamic equilibrium. Dynamic equilibrium. Dynamic equilibrium. So what's interesting about these is that they, inertial vectors are often called inertial forces, as they measure the resistance that particles offer to the motion, i.e. changes in speed or direction. So when I say, actually I should point out that this whole thing doesn't equal the inertial vector, just negative ma is equal to the inertial vector. So we often refer to, what we can say is inertia. If you remember back from Mr. Nye, he told us that inertia is a property of matter, right? I'm so sorry. Mr. Nye told us that inertia is a property of matter, and we can actually consider it as a vector of its own on a free body diagram. So notice, in statics, all you ever did on free body diagrams was apply forces, but we can even, if we wish, apply, we can apply the inertia, the mass times the acceleration, as a vector. And what this kind of represents is, inertial vector represents the resistance of an object to a change in momentum. The inertial vector represents a change of or an ability's, so I should say, sorry, I can't talk, I need to get more sleep. Represents an object's ability to resist change in momentum. Change in momentum. All right. So these can be useful, but they're really not really true forces. They're not the same kind of forces that you would see in, say, statics. So they're not like something like gravitational force or contact forces, etc. Okay, so let's think about this. Let's look at free body diagrams and kinetic diagrams. Free body versus kinetic diagrams. Or kinetic systems. So free body diagrams and kinetic diagrams. And kinetic diagrams. So it's basically the same thing as in statics, except slightly different. So for the free body diagram, this is just like in statics. No change. You're simply drawing the forces draw forces, object, coordinate system, etc. Coordinate system, etc. So, if you want a kinetic diagram, however, a kinetic diagram shows the accelerations on a system, or will show the inertial forces. Shows the inertial forces on an object. Okay? And essentially the free body diagram should produce the final vector sum, the same vector sum, as the kinetic diagram. So, something like this. Let me work through a quick example here. So, example, kinetic versus free body diagram. And free body diagram. So let's say I had a block and a ramp. Let us say I had a block and a ramp. I like blocks and ramps. They're happy blocks. They don't rotate. They're nice and happy. They're made of happy trees, made from happy trees. So let's say you had something like this. Maybe a pulley here. And we have a cord that comes up and does this. And I will say this is a 15 kilogram block, so this is given. This is 225 newtons. This is a 15 kilogram block, and the angle here is 25 degrees. The angle here is 25 degrees. All right, so let me draw the free body diagrams and the free body diagram and the kinetic diagram. So this is then going to be equal to, I'm going to use my x and y axis kind of like this. Actually more x and y, sorry. X and y. So solution here. So if I draw the block, I'm going to have mg pulling down, the normal force pushing out, the frictional force pulling down, and the 225 Newton force pulling up. And so this is the free body diagram. And this would be 25 degrees. And then the kinetic diagram would be something like this. I would have MAX like here, and MAY here. And these two are fundamentally equivalent, because this all comes down to sum of forces. This is basically sum of forces equals mass times acceleration. So I could go and do a bunch of trigonometry, find all the x components of each of these, and they would have to be equal. The x components on both sides will have to be equal, and the y components will be equal as well. Okay, let's see. Here. What else can we do? Now, I will actually mention, maybe in case, maybe as a bit of review, maybe I will actually list the steps for the whole thing. So the whole thing, kinetic and free body diagrams. And free body diagram steps. One, we're going to isolate the body, make any cuts if necessary. Two, use label axes. Label axes. Three, apply forces. Four, replace supports with forces.
It's like the ramp.
Yeah, like the ramp, yes. Or like a simply supported beam or something like that. We would replace say the pin support with two forces, an X and a Y. So replace supports with forces. 5, have dimensions on there. And 6, get the kinetic diagram. All right. Let's work through another example here. So say I have the following, another block on a ramp, but this time I have a example block pulley system. On ramp. So I have my support body. I have, oh, this is going to be real fun. All right, so let's see what else we can do. So I have 3 pulleys here, and maybe I'll have a block here, and then the cord between them will go in light blue. So it's going to come around this way, down here, around here, and back down. And then the dimensions here, this angle is going to be 25 degrees. And this one here, well, actually, it's going to be measured from the existing surface here. This is 15 degrees. So I'm given all this nonsense, and I wish to find the dynamic or the kinetic and free body diagrams. All right, so let's draw this out. Oh. So free body diagram. Okay, and this is block B, by the way. This is block B, and this is going to be point A.
Point A or block A?
Let's see. I think it's going to be point A. So the free body diagram is going to have here NB, F, friction, FF at B, FF at B, the frictional force at B. It's going to have tension, the tension in the cord. It's going to have the tension in the cord going this way from the pulley. It's going to have, as the pulley goes around, it's going to have tension here and tension outward. And then another tension outward here. Then a weight in the middle, mg. The N1 on this contact surface, and then a frictional force 1 as well. FF1. Oh, dang it. And this then is going to be equal to the kinetic diagram of, well, that's just mass time acceleration vector. So that's going to be MAY equals 0. Then I would also have some sort of MAX, which would not be equal to 0. Which is also 0. Let's see, what else? Okay.
MAX equals 0 as well?
Huh?
MAX equals 0 as well?
MAX, would it be equal to 0? No, MAX would not be equal to 0. The only reason MAY is equal to 0 because this thing is going to be sliding up and down along the ramp here. Yes, we could draw. Yeah, actually, that probably would be good. Let's draw the coordinate system here to be consistent. Let's draw our coordinate system here, x and y, and x and y, like so. All right, and this is basically the same process that we would use for others. Okay. Now, what if we had more of a rotational system? Or maybe not. Okay. Actually, maybe. Okay, let's look at this. Let's look at another example. Here. Let's look at another example of drawing these and say, okay, let's say I had a pin and a collar. So there's a rod attached here. A rod and a collar. That's sort of an end cap, but then there's a big collar that can rise up and down. So there's a big sliding collar that can slide up and down on this shaft here. And then there's going to be some labels. Let's make this r. Let's make this the origin, and then let's make this theta. And so all this is given, and I'm told to find, draw kinetic and free body diagrams, FBDs, assuming motion in vertical plane. Let's see, assuming there's friction acting. Well, actually, let me just give a series of assumptions. Assuming 1, and these are all occurring at the same time. 1, there is friction. Let's see. Friction exists between rod and collar. Between rod and collar. Between rod and collar. 2, motion is in the vertical plane. Vertical plane. And 3, theta is increasing. Is increasing. And theta is increasing. Oh my god, that was really bad. Increasing. So we're assuming theta is increasing. Okay? So I'm going to define a different coordinate system. And this is going to be a little bit different. And I'm going to define a radial and a angular coordinate system. So I'm going to define a coordinate system. So solution here. I'm going to define a coordinate system of both r and theta. So I'm going to use the vectors er and e theta. E theta. We're effectively, so theta is going to be changing, but what this really comes down to is this is more of a centripetal or a normal or an orthogonal line axis. This is towards the center, and this one is going to be along perpendicular to this. So this is like a radial. So this thing will move back and forth, and this thing might move up and down, but this is going to be always pointed toward the radius, and this is always going to be perpendicular to it. The E is a unit vector. If you remember that from from last time when you were looking at unit vectors along of curvilinear motion. And then here, let me show you this is going to be the free body diagram first. So I'm going to have theta indicated maybe here. This thing is at theta here. Because if this is theta, then this is theta. And the forces on here would be, because remember, the reason it told us to assume vertical motion is because I need to know which way to point my friction. If this thing is moving upward like this, then the friction will go opposite that. So this is the force of friction. And then the normal force would act here. And then mg will be pulling down. mg will be pulling down. And all of these must be equal to the inertial diagram. This will be equal to the same block, or the same collar, I should say. This isn't a block, it's a collar. And this would be the inertial forces MAR. So that would be the acceleration in the radial direction, or the radial component of acceleration at some time, and MA theta here. MAR and MA theta. All right, so let's look at this here. And let's see. So let's consider that. All right, and I think that might be a good place to take a break. We'll come back and look at some more examples shortly after a quick break to recharge, etc., etc. Thank you.